Okay. Thank you very much for the introduction, Saskia, and general, ladies and gentlemen. As Saskia said, I would like to speak about the performance enhancement by GZ protection, and in particular I will focus on non-invasive objective methods to evaluate GZ protection. Next slide, please. A reliable anti-G protection is a sine qua non for every pilot in order to successfully fly the modern, highly agile fighter aircraft, which are characterized by considerable, extremely high maximum G forces, extremely high G onset rate, fast transitions, and sustained exposures. And with continuing evolution of aircraft, of course, the anti-G protection has to improve too, and continuously, and therefore, of course, the German Air Force Institute of Aviation Medicine follows the studies which are dealing with the enhancement of G protection. Next slide, please. There are several aspects of assessing the efficiency of an anti-G suit. Without any question, the main criterion is the suitability of the suit to prevent a G-induced loss of consciousness. There are, however, other aspects which have to be considered and quantified. For instance, the impact of the suit on the pilot's performance and on cardiovascular function. And also noteworthy are the wearing comfort, especially if 24-hour missions are concerned, and we have side effects related to the suit's weight and thermoregulation, and possible adverse effects if the positive pressure breathing is used, and the speech intelligibility. Furthermore, we have to look for the appearance of arm and foot pain and the creation of G measles. And last but not least, the question of which mental valences are still available under IGZ to fulfill the mission has to be answered. Next slide, please. So in my presentation, I would like to concentrate in the evaluation of the suit's impact on the pilot's physical performance and cardiovascular function under high Gs. And in order to obtain objective, reliable, and valid data which could serve as a decision guidance for the validation of the efficiency and the improvement of anti-G suits and measures, we have to do the first step first, and that is to test clinical established non-invasive methods to characterize cardiovascular function regarding their suitability under high G loads. In high G environment, the non-invasive hemodynamic monitoring is highly challenging. Even though the recording of an ECG is possible with only little disturbances, and we have information about the heart rate, the cardiac rhythm, and for instance, for conduction disturbances, this statement is not true for blood pressure measurement already, and if so, only in the lower range. And we have no idea about the control variables of the circulatory regulation in a non-invasive manner. And that's why we decided to look for methods which could be used in this human use centrifuge, and which could be suitable for hemodynamic monitoring under GZ. Next slide, please. So among the methods which we had available, we decided to look for the pulse oximetry first. It is a method which was developed by Takuyo Ayuyagi in the 70s already, and meanwhile became a clinically well-established method to measure the oxygen saturation of the blood using a pulse wave dependent spectrophotometric method. And in order to measure the oxygen saturation of the blood, the conventional pulse oximeters use photoplethysmography. It's a method which was developed by Hertzmann in the 30s, especially for measuring changing of blood volume changes. So usually the pulse oximeters use two wavelengths penetrating the tissue with red and infrared light, while a photodetector measures the amount of light absorbed. And thus in the signal which the photodetector receives, we have, besides the oxygen saturation, other information about the circulatory situation. For instance, we have information about cardiac contractility and venous return, and so we try to use that at the Human Use Centrifuge. Next slide, please. The normal photoplethysmographic signal contains of both. We have an AC, a so-called AC, or an alternating current portion, and we have a DC or direct current portion. And the AC portions was under the signal modulations which have been described first in the photoplethysmographic signal, and the signal intensity can most easily be determined using the amplitude of this AC portion. In contrast, the DC portion is primarily influenced of the degree of vascular bed filling, and a reduction of the degree of vascular bed filling is, as we cannot expect under G-load, would result in an increase of the signal released, or the light released by the tissue. So, next slide, please. All experiments took place in the Human Use Centrifuge of our institute in Königsbrück, and the data I'm going to show you are selected from different comparative studies on different anti-G suits, and the setup of the test station was always the same. We had our test subjects with a reflectance pulse oximeter sensor on the forehead, and this sensor was hooked up to a preamplifier in the gondola, and afterwards to the workstation computer. Workstation computer in the upper story of our control room in the Human Use Centrifuge. And we had an extension card in the computer for queuing the sensor and for digitizing the signals. And we had, of course, a software for presenting the signals and for recording them. And we had a special software for the analyze process of the biological data. Next slide, please. So now I would like to start to show you what we did with the AC and DC portions of the photoplethysmogram in gradual onset runs, and how we try to determine the efficiency of the anti-G suits under these conditions. Next slide, please. So we had 45 subjects participating in the studies. 35 of them have been pilots, 10 of them have been novices with no experience in the Human Use Centrifuge. They were pretty similar with respect to height and weight, but they differed, of course, in the age. We looked at different anti-G suits. We compared the traditional aircrew equipment assemblies versus the Libelle G Multiplus from Autoflug, and then we looked at an enhancement variant of the Libelle G Multiplus and at the aircrew equipment assembly without breathing protection. So next slide, please. We asked the test subjects to undergo a linear profile, and we recorded the pulse wave, and here you see the original recording of amplitude changes of the pulse wave during gradual onset run, and the onset rate was 0.5 Gs per second. Next slide, please. So what did we do with the signals? Here you see the evaluation of the AC portions of the pulse wave. First of all, we determined the point in time at T0, which was the beginning of the gradual onset run, and we looked at the amplitude at that point, and then we looked at the time and the amplitude when the pulse wave reached its maximum, and we calculated the percentage increase compared to the baseline values. Next slide, please. Here you see the results. Independent of the suit we used, there was always a considerable increase of the AC portion during the gradual onset run. Next slide, please. And we were a little bit wondering about the same qualitative reactions of the novices, novices and pilots, but the big differences in the quantity, the same was the case when we used aircrew equipment assembly, which is not seen here. And next slide, please. And the cause for that could be found in the pressure volume diagram of the aorta. This volume curve shifts to the right, and it's getting steeper with aging, and that means that the heart has to build up higher pressures to get the same volume out. So, and that was the explanation for the big differences we found between novices and pilots. Next slide, please. And when we looked at the correlation between the amplitude of the AC fluctuations and the age, indeed we found a correlation between age and the AC, even if it was weak. Next slide, please. Interesting was also the reaction or the comparison of the aircrew equipment assembly and the aircrew equipment assembly without any breathing support, and this argues the higher reaction of the aircrew equipment assembly with breathing support argues for the fact that there is a bigger strain of the heart during positive pressure breathing. Next slide, please. So what did we do with respect to the evaluation of the DC portions of the pulse wave? Again, we determined that the point in time at the beginning of the run, and then we calculated the difference against these baseline values during the course of the experiment. Next slide, please. And what we found, you can see here, we had an increase of the DC portions during the run, and what you see is that those persons which had the higher relaxed G tolerance seem to be to have the lower volume shifts, and this became clearer. Next slide, please. when we divided the groups into a high performer and a low performer by the median of the relaxed G tolerance. And here you see clearly the group with a higher G tolerance had the slower increase of the DC portions and the smaller volume shift. This was the case in the acro equipment assembly. This was also the case in the Libella G multiplus suit. Next slide, please. Of course, gradual onset run are interesting, but much more interesting are rapid onset run, because they are much more similar to operational conditions. So we try to expand our method also on rapid onset runs and use the DC portions of the PG to determine the efficiency of anti-G suits. Next slide, please. So for that we used an exhaustive simulated aerial combat maneuver, which where the test person was asked to take as much as possible GZ during a run of 150 seconds. And we compared the traditional anti-G trousers, the Libella G multiplus, with the acro equipment assembly and with the G-Ruffer, which is a non-commercial anti-G suit where we were able to follow the testing procedure, and it is made by a Swiss company. So here you see the parameters which we recorded and analyzed. Of course, we looked for the G load, we had the ECG, we had the heart rate, and we looked for the behavior of the AC and DC portions. Next slide, please. The performance data were determined using the time integral over the G values, as you can see it in this picture on the left, and by integrating between selected G values. And here you can see clearly the performance of the G-Ruffer suit was much better than the performance of the acro equipment assembly, the anti-G trouser, and the Libella suit. Next slide, please. So then we looked at the mean G load reached during the whole run, and also here you can find that the mean G load reached was the highest in the G-Ruffer suit. It was the next suit was the acro equipment assembly, followed by the anti-G trousers and the Libella. Next slide, please. Here you can see the time course of the mean heart rate, the time course of the heart rate, sorry, and the mean heart rate reached over the run, and the highest values were reached with the anti-G trousers. I think that's was to be expected, and we had the lowest values was a Libella, but we have to keep in mind that the performance with the Libella G suit was lower than with the acro equipment assembly and the G-Ruffer suit. And we had the highest heart rate around these three anti-G suits with the acro equipment assembly. Next slide, please. Then we looked at the mean changes of the DC portions, which are an indicator of vascular bed filling changes, and compared to the baseline values, and we didn't consider the different G that reached. So, and you see, it's not comparable when you have so different performance data. So next slide, please. We looked at the mean changes of the DC components compared to the baseline values as a function of the GZ reached during the maneuver, and you can clearly see the suit with the lowest value. Next slide, please. is the giraffe suit. We call this index the volume loss index because it is giving us an idea about the volume shift we observe. And here's a formula for that. And with that index, next slide please, we have an objective measure for the efficiency of an anti-G suit. Next slide. And this is independent of the cooperation of the pilots. And even if they don't have a good day, we can calculate this index and can make a decision about the efficiency of the suit. Here's the formulas behind this index. We determined first the baseline values, and then we looked at the values during the run and tried to get them normalized by the G performance. Next slide. In conclusion, we can say that our studies proved the method of photoplethysmography to be suitable to obtain relevant information regarding the cardiovascular regulation in a high G environment. Changes of AC and DC portions of the photoplethysmogram due to G loads can be used as an objective indicator for the efficiency of anti-G garments and maneuvers. And by calculation of a volume loss index, it is now possible to reveal even small differences in the performance of different anti-G suits and to make them objectively verifiable and comparable. This applies even in the upper GZ range and independent of the cooperation of the pilots. Thank you very much for your attention. Next slide, please, for your attention. So, do you have questions?